Hello, welcome to Digital Circuit Design course. Today I'm going to introduce a new topic, state machine. I assume that you already have some idea how to design combinational circuit and sequential circuit from specification. You have some idea about uh, latch and flip-flop, that is the clocked latch basically. You have understanding of synchronous circuit, asynchronous circuit, some application of flip-flops like frequency divider and counter, synchronous counter, asynchronous counter. So we already covered this part, right? So 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 let's start today's topic, that is the state machine. So state machine is a concept which can be employed to design any digital system in a very generalized way. Okay, so state machine is not a basically a machine in that sense that what we mean by electrical or mechanical machine. Rather, it is a mathematical model of computation. Okay, so it is an abstract machine or abstract theoretical model which is used to design the digital system. So we'll define state machine as a system or circuit which has several states. Okay, and that it has to have some finite number of states in which it can exist. Okay, and it may has clearly defined a set of inputs which will steer the system from one state to another state, and each state also may produce some output. Okay, so for a state machine it is obvious that it will have some finite number of states, so that's why it is often called finite state machine. Okay, finite state machine also because it has some finite number of states. Okay, and it has clearly defined it may have some input or it may not have some input, it may have some output, it may not have some output, but obviously it will have some finite number of states. Okay, so what is the characteristics of state machine? So state machine in general, the behavior of state machine will depend on the present state and the external inputs. Okay, but these external inputs are again optional. Some state machine may have external input, some state machine may not have external input. Okay, so next state of a state machine always depends on the previous state, and there may or may not be external inputs that I already said that, and there will be definitely output, right? Because but in the sense that I'm not talking about that, because when you are designing a system it will produce some output. Obviously it should produce some output, otherwise how you can know that, how will match the specification, because you are designing the system for some to generate something, right? So it will always have some output, but you may not have external output. Sometimes the state itself may be the output. Okay, so in the last slide I told that the state machine may have output or may not have output. There I must what I mean is that the state machine might not have some externally defined output, but maybe the state its state itself may be interpreted as output. Okay, so state machine is so we will discuss this part, that when the some special scenario when there is no external output but the state itself may be treated as output. You already know what is this, so we'll discuss it. Okay, so so now let's talk about the synchronous state machine. Okay, so state machine can be of different types. One is called synchronous state machine. We'll mainly focus on synchronous state machine. What you mean by synchronous state machine is that it will the state of the system means, suppose let's take an example. mm, Synchronous state machine is like mm, suppose you have one state S1. You have a system which having three states, suppose. So it is having three states connected like this, means it has three states, S1, S2 and S3. So the system will change the state of the system will, so this is a FSM, right? It has finite number of states, so we'll call this as FSM, right? So it has finite number of states, so it will go from, suppose it starts from S1 state. Okay, it start from S1 state and the state will change to S2 when a clock will be triggered. Okay, means the system itself may have some external input, suppose X. It may have some external output Z, but it is always triggered by some clock, and it had some internal state S1, S2 and S3. Okay, and so it will triggered by clock means its state will change from S1 to S2 or S2 to S3. It will determined not only by input X but also the clock, right? You know already, because suppose in flip flop what happens, suppose one example is flip flop, right? Suppose you take a JK flip flop, right? You take a JK flip flop and suppose its output is at Q is at 0, right? And now if give the input 0 and 1, suppose Q is 0 and Q bar is 1. So if you give the 1 input, it will go to state 1, but suppose it is triggered by a clock, it is a positive edge triggered, suppose, then it will goes to the clock to the state 0 when it will toggle only when the clock is positive, at the positive edge of the clock, right? So it is triggered by the clock, so it is going, its inputs are JK, but it will not change its states until the clock is positive, right? Positively triggered, right? Because it is positive edge triggered. So synchronous state machines are those state machines which are triggered by clock, right? And so that is the definition. So synchronous state machine are the state machines which are it has some internal states, number of internal state, and it can change its states based on the inputs. So it will have some X input, but also it will change the states. Its transition will, so S1 to S2 transition will determined by X, but it will only triggered by clock. So it will change its states only based on the clock signal, but it will be determined by the clock, by the external inputs. So what transition it should take, whether S1 to S2 or S1 to S3, right? So this is one example, one little bit So example, we'll discuss more details and later on this lecture. So let's see. Let's see. So transition is determined by the present state and maybe also by the external input. Again, why I'm putting here maybe here, because external inputs are optional for defining a state machine, right? It may happen that the state machine only has some predefined state, finite number of states, but there is no inputs, but it is changing its states based on the triggering, right? It may happen. So, but in general, there may be some external inputs. So, this transition is determined by the present state, obviously, and maybe also the external inputs. And state transition is not necessary in each clock period. Okay, so it may happen that the state machine is staying. So here, just look at here. So here, suppose S1, S2 and S3. It may happen that the system remains in state S1 for a long period of time, right? Suppose based on the input, suppose inputs are such that it is staying at the same state for a long period of time, so it's not necessary that it should always change its states, because its clock is it is giving a positive transition, right? So it may hold its states. Okay, so but in general it will be determined by the external inputs and it will triggered by clock. Okay, so state transition will be determined by the external inputs and the present state, but it not necessarily that it will always change its state in each clock period. Okay, and output will be determined by the present state and external inputs, right? So then this equation is very important. The next state will be a function of present state and external inputs, but this external inputs again optional, because we are defining the state machine in general. So there may be some external input, may not be external inputs. Output will be function of present state or and external inputs, but this external inputs again optional, because finite state machine always have some predefined finite number of states, but this external input is optional, right? We'll discuss more. So let's go to the next slide. So here is the example. So why this is important? So why this state machine concept of state machine is important in designing a digital system, particularly the sequential or synchronous digital system. Just look at this example. So let's take, this is a digital system with input x. Suppose x is n bit and z can be output z, that is of m bit, and x is n bit. So it can be any bit, number of bits, right? You can understand. So input is x, output is z, and suppose it has four state, S0, S1, S2 and S3, and behavior. So state is S, defined by S, so it has 4 states. So there is 4 state, means I need 2 state variables, right? So if I want to digitally store them, I need, so 4 state means 2 variables, 2 state variables. Suppose AB, because 4 states, 0 0 0 1 1 0 1 1, right? So the behavior of the system, is defined by this diagram. Means so initially suppose system is S0 and its output is z equal to 0, so it's 1 bit output. Okay, and I'm also assuming this its input is 1 bit. So if x is 0, then it will remain at that state it will so mm, this circle is showing this red circle over here, this red circle, this is showing that, it is actually showing that if input is 0 at state s0, it remains at that state s0, it does not change its states, it will stay at the state as long as the input is x is 0. But when the input becomes 1, x becomes 1, it will change, the system change its states from s0 to s1, and but at the triggering, but this transition will triggered by the clock. Okay, so this is the behavior, this way we have described the behavior of the system. So at the each state you can see there is two possible inputs. One is x is either 0 or 1, because we have assumed that the input is 1 bit. So at S1 also it can have x equal to it can have x equal to 1 or x equal to 0. So you can see if x equal to 0, then it will go to S3, and if x equal to 1, it remains at S1 state, so it does not change its state. So this way we can describe the complete behavior of system, and we can represent this digital system, the behavior of this digital system, using state diagram, right? So you can see that only system produce output at state S3 z equal to 1. So here you can understand, but only the output of the system here, output of the system is depends on the present state only, right? Like when system at the S3 state S3, its output is 1. Otherwise in every states you can see that its output is, in any other state output is 0, z equal to 0. Only here your output is z equal to 1. Okay, so this is description, it's just an example. Okay, it's not, it's just an example of a digital system, it's an instance. Okay, so now how can we design this state, how can we design it, this system, using some hardware model, right? So this is the specification given, we represent it using state diagram, very easily we can represent that, right? So now how we can design it, so how we can design the hardware model, generalized hardware model. So now I will discuss how we can design the generalized hardware model. So as already I told you that, let's look here. So already I told you that there are 4 states in this model. In the state diagram you can see there are 4 states. So if I want to store them digitally, I need 2 state variables. Let's take them A and B. Okay, and so you know how to store the bit. So to store 2 bits, so I need to store 2 state variables, I need to store 2 bits, so I need 2 D flip-flop. So here I need 2 D flip-flop. So you can see here I need 2 D flip-flop, right? So this is my system. This is my system. It is taking external input and it is producing output, and it has a present state and it has a next state, right? It is going from present state to next state. So you can see here that, so this D flip-flops are triggered by clock, right? And triggered by clock. So after each transition, next state will be function of this external input and the present state, right? External input. So next state, this next state will be function of this external input and present state, right? So we have to design a combinational logic. We have to design a combinational logic so that I can generate the next state using the present state and the external input, right? And also output will be the function of external input and present state. Okay, so this is a generalized model. But when we generate when I get the present state and external input, I can generate the next state, but that will not be reflected, the next state will not be reflected as the present state until and unless the clock is triggered. Okay, you know triggering, right? Either positive or negative is triggering, whatever the triggering mechanism you follow. So it will not change its state, and that's why these flip-flops are there. So this is actually my sequential part, this is my memory part, and this is my combinational logic part. Okay, so state machine, so this is a generalized model. So this state machine has two parts. One is this sequential part and this combinational part. So this combinational logic basically computing the next state using the external input and the present state of the system, and output also. It also computing the output using the combinational logic. But this next state is changing to the present state. The system is going from present state to the next state based on this sequential logic, based on this triggering, clock triggering. Okay, so you can understand, right? So this is a generalized model. But again I am saying this external input and output is optional. So because this, for this system is fine, because for this state diagram this is all right, for this state diagram exactly this is fine. But suppose there is some state diagram, there is no external input, there may not be some external input, there may not be some external input, there may not be any output, there may be some external input, there may not be output, there may be output, there may not be external input. So this is a generalized model. Okay, so but this state will be there obviously, because this is a state machine, it will have finite number of states that will be defined, but external input and output is optional. Okay, so what is the takeaway points from this discussion is that, so any digital system, so why we are discussing is because that any digital system can be modeled as a state machine. Okay, so if you take a combinational circuit, so you will say what about combinational circuit? Yes, combinational circuit is also a state machine. Why not? Because combination system can be treated as a state machine with only one state. Okay, it has only one state, and if you have set of inputs, it will produce a set of outputs you will define. So it will not change its states, there is no triggering, so it is completely defined by its inputs and outputs, but it is having only one state. What about flip-flop? Flip-flop is also a state machine. It has two states. If you states either 0 or 1, right? Because, and so it is a synchronous state machine with two states. Now the special case is counter. What is counter? Is the counter is a state machine? Yes, obviously counter is a state machine, and it is a special type of state machine that I am talking about. That is, it don't have it don't have any external output or external input, right? It only has states, it only has finite number of states, but it is a state machine. Why it is state machine? So let's take a 3-bit counter, mod 6 counter. So 000, 001, 010, 011, 101 and 100, and again 000, right? So 1 2 3 4 5 6, total 6 states, right? 0 1 2 3 4 3 5 and 6, right? And again 0. So it has 6 states, right? So since it is a 6 state, so I can represent it like this. So this is my state 1, state 2, state 3, state 4, state 5, state 6. And what is 000? These are state variables, because I have 6 states. So I need 3 variables, right? I need 3 variables, A, B, C, suppose. And so the counter is a special type of state machine which don't have any external input. So it basically changing its state with each clock period, which each clock pulse, right? So, and it has no external output also, and its state variables, so its state variables is 000 or 001 or 101, anything. Its state variables are basically interpreted as output. So it has no external inputs, and its state variables are interpreted as output. Obviously it has output, but the state variable itself interpreted as output. So this is my counter. This is a 3-bit counter. It's triggered by clock, and it has 3 state variables which are interpreted as output. Okay, so this counter is a special type of state machine. It is also a state machine which has no external inputs, and its output are treated as state variables, right? So output are basically the state variables are treated as output, right? So what is the design strategy of state machine? So it is pretty simple. So now you have a system behavior will be given to you, a system specification will be given to you, right? A specification will be given to you, and you have to represent this using the specification. You represent your system using a state diagram, just like this one. You have to represent, right? You have to represent. Next task is to implement the state graph using hardware, right? Implement the state graph using hardware. So this is a 3-step process. So first specification, and then state graph, and then the hardware, right? So so once you get the state graph, this transition is very straightforward. So this translation from state graph to hardware is very straightforward. You only need to design it using the excitation table and combinational logic. Excitation table of the flip-flops and the combinational logic, right? We'll discuss various examples of how we can design the hardware model from the state graph, right? So in the following lectures we'll discuss this part with more details. So let's take a summary of the discussion what we have discussed today. So state machine, so basically state machine is a new way, or it's a new viewpoint in which we can look at the systems. So it's a new viewpoint, basically. It's a new viewpoint, or new way of analyzing the system. It's a new way of design a system, right? So So any system can be, any digital system can be reduced to a state machine. Any digital system can be modeled as a state machine. Okay. And whether it is combinational or whether it is sequential, that doesn't matter. And but particularly we'll focusing on synchronous state machine, which is which will be triggered by clock. So each transition will be triggered by clock, so which we have mainly focused on in this lecture. However, circuit, but it not necessary that each transition the state will change, right? It may happen that the circuit is a system is staying at the same state for many clock cycle, right? And the state machine may not have external input or output. An example is counter that we have already discussed. And what is asynchronous state machine? Asynchronous state machine that we have not discussed, which is a little more difficult to analyze, because those are not triggered by clock but triggered by event. Okay, so it means the system changes its state from one state to another state when a particular event occurs, and then if again some particular event occurs, it goes to another state. So it is triggered by over, and it is little more difficult to analyze, so we are not going to discuss that right now. We'll mainly discuss right now the synchronous state machine, and later on I will discuss, if time permits, the asynchronous state machine. Okay, and in the next lecture we will mainly focus on the how we can, from a given state graph, how we can translate it to a hardware model. Okay, that I'm going to focus in the next lecture. So that's all for, I guess, for today. And please follow these slides, follow the lecture, and let me know if you have any doubt regarding the regarding this lecture or any other concept in digital system. And stay tuned for the next update. That's all. Stay safe and keep on learning. Goodbye. Thank you.